So for the new content today, we may not get all the way through it because the examples took a bit longer, but hopefully they were instructive. We're going to talk about non-ideal systems. So if we had to vote which of the two systems, vapor or liquid, is going to be the one that has the higher tendency of being non-ideal, which would we say?
Liquid.
Why is the liquid?
Because the molecules are closer to each other and have more
Exactly.
opportunity to interact.
So this is a fun little example that I put together. I want us to visualize the density of liquids. And how we're going to do this is that every single one of us in the room is going to be a water molecule. So the question is, what's that?
Are we going to do a group hug?
We're going to get real close. Well, that's a good example. I should calculate how many people in and how small of a space we have to fit into for us to be the same density of a liquid. But what we're going to do is, if water molecules were people-sized, the key questions: 1, how many people would be in this room if we were an ideal gas? And 2, how many people would be in this room if we were a liquid? So we're going to take guesses right now. So, if we were an ideal gas, how many people are in this room? Shout out some numbers.
So are you saying like there's
I'm
another
gonna go with like a
adjacent to
hand,
this that
maybe like
are,
an arm.
we're talking like unit cell wise?
No, so we're this, water molecules are going to be grown up to the size of us, of people, right? So every one of us is a water molecule. So if we were a water molecule exhibiting the pressure against the wall of an ideal gas based on the number of collisions and our temperature, how many people would be in this room to maintain that pressure? Okay.
Like half.
Okay, so we got the half. What else we got?
Less than 1.
Less than 1. Anyone want to venture higher than that?
2.
2. Okay. Stop there.
Should have just said more than 1.
I know. Right?
Cover all.
If we were a liquid, let's get some guesses.
Less than 1.
You still think less than 1?
I
I'm gonna go with like 40.
40?
200.
200?
I said
What's that?
1,000 people. 1,000.
1,000.
Ooh, let's do another order.
Okay, so we've got a good collection here. So how we're going to do this is we're going to use the Peng-Robinson B excluded volume. Because ultimately, there's no good way to estimate the size of a molecule, right? Because really you're looking at an electron cloud. An electron cloud is really just a probability distribution. So where you draw that boundary is kind of arbitrary. So the model that we're going to be using is the Peng-Robinson excluded volume. So a quick thing here, so for water, in the Peng-Robinson equation state, and this is based on the critical point of all fluids, its B value is equal to 1.898 times 10 to the minus 5 meters cubed per mole. So this is effectively, it's not exactly the volume that the molecules occupy. What's called the excluded volume. So what that means is that if I have a spherical particle, and in fact, effectively all cubic equations of state assume spherical particles. They introduce this thing called an eccentric factor, and they say it accounts for like, non-spherical particles. That's just not true. It's really just an additional tunable parameter. Because you can look at something like carbon dioxide and carbon disulfide that are exactly the same, and they have totally different eccentric factors. But anyway, so if you have a particle in a sphere that has a particular radius, and another particle here, right, there's a region where the center of mass of this particle cannot cross, otherwise the two particles will overlap, right? And this is sort of an ultimate exclusion principle, right? You can't have electron clouds overlapping because of the, what is that one called? The Pauli exclusion principle, right? Because you can't have the two electrons occupying the same state. So effectively, what the excluded volume is then, is you draw a ring around the first molecule with a radius of 2r. meaning that the center of mass of the second particle cannot cross this ring, otherwise two parts of them will overlap. So if the center of mass is here, this is not trying to scale super well, right? You could see that the center of mass when it crosses this line will go over there. So the excluded volume is in fact 8 times the volume of the pore, the volume of the particle, right? So the volume of the sphere is 4/3 pi r cubed. The excluded volume is going to be 4/3 pi 2r cubed, which is going to be equal to 8 times the volume of the system. Does that make sense for everyone? So the volume of an effective sphere for the size of a water molecule is 1/8 of this here. So what we're going to say then is I derived a little equation here that just says that the percent of free volume, meaning the volume that is physically not occupied by an actual molecule, is going to be equal to the fluid density minus the volume occupied by the actual particles themselves, which is B, the excluded volume, divided by 8, normalized by this, and then of course times by 100. All right. So, ideal gas at 25 degrees C and 1 atmosphere, its specific volume per mole. So in different units, just to make this a little bit, 24.5 liters per mole, better units there. As an example, saturated liquid water vapor is at a lower pressure, right? It's going to be at about 3 kilopascals, so its density is even going to be lower. This one's going to correspond to 0.9215 meters cubed per mole, which is equal to 921.5. Right, so a lot of volume occupied because the pressure is so low. That's for saturated. Now for a liquid, we have actually 2.21 times 10 to the minus 5 cubed per mole. Now these are values predicted by the Peng-Robinson equation of state actually. And this corresponds to 22.1 cubic centimeters per mole. So for water actual, this is 18.0 cubic centimeters per mole. So it's okay, it's not too bad, right? That's the prediction for the Peng-Robinson equation of state. Okay, so for the system, we have ideal gas, saturated vapor, and liquid, and we have percent free space. How much space is free? So for an ideal gas, the free space that is not occupied by physical particles is 99.99% free. For a saturated vapor, because the pressure is lower, is 99.9997% free space. And for a liquid, it is 89.3%. So about 11% is physically occupied. But if you times that by about 8, right, that tells you how much volume is being physically excluded from it. So now the last question that we need to sort of answer our problem goes back to how big is a human? What's the volume of a human? What's a good way to estimate that?
Cylinders. 6 foot.
I think
Okay, this is what we like to call a Fermi problem.
Like an ideal human, they design at 6 foot.
Yeah, Michelangelo's David, right? How would we estimate what the volume of a human is?
Make it a cuboid. So we have length 6 foot, like
I've got a much easier way to do it.
Put a human in a bathtub and
We could do that. Humans have buoyancy. I'm going to do it with mass.
And
So-
density.
Yes, mass and density. So what I'm going to say is blank meters cubed is equal to 170 pounds as an approximate size for an average human. So that means that 2.2 pounds is equal to 1 kilogram. 1 kilogram is 1 liter of water. And 1,000 liters is equal to 1 cubic meter. Back of the envelope calculation. In your laboratory work, you never measure volume. Don't ever measure volume if you don't have to. Always do everything by mass. So that gives us the volume per human as 7.73 times 10 to the minus 2 cubic meters. So not that big, right? Really far away from a cubic meter, which would be a large person. So, the number of people in the room. So I'm going to do a little bit quick stoichiometry here and say that the number of people is going to be equal to the volume of the room multiplied by 100 minus the percent free divided by 100 divided by the volume of a person, right?
Yeah.
So this is how much is occupied by objects multiplied by the room divided by that. That'll give us a number of people, right? Cubic meters per person, so we'll get number of people as our unit to pop out. So for this room, I estimate that it's about 2 by, what did I say here? 2 by 10 by 10 meters cubed. 200 cubic meters. Does that sound fair to everyone? About 30 feet by 30 feet, or is the room bigger than that? 2 meters, no, that's not, maybe that's a little small. Maybe this room is bigger.
It's like 3 meters.
Okay.
Oh, maybe I'm underestimating it a little bit.
Yeah. Still,
All right.
Still needs to be difference.
So, ideal gas. The number of people in this room, if we are an ideal gas, is 1/4 of one person.
Oh, nice.
Okay.
So maybe like a leg or a torso. Okay.
One leg.
For the number of people in the room, and I counted, there are approximately 40 seats in the room. Okay, 40 chairs, so a full room with 40 people packed in there. We would have 278 people in this room if we were a liquid. And that's only considering it being 11% occupied. But another thing to consider though is even solid water in the form of ice, it's actually less dense, right? So even when you have a solid material, it's still mostly empty space. So the key thing here is this is about a factor of 1,000 different. Now imagine that, I guess we can imagine this quite easily. Imagine we had 278 people in this room. I suspect we're not going to want to be super close to one another,
This is not
right? So we don't have electrostatic interactions like water molecules do, but we have sort of personal space interactions where we don't want to be really, really close to other people, right? So when we have a really dense packing of a fluid, that's going to severely affect our ability to calculate accurately how everything is going to behave. Right, so even with a solid though, let's say we have spheres and you pack spheres as tightly as possible. Does anyone know what the percentage packed of spheres is maximally?
Oh, there's a equation for this.
Yeah.
Percentage. Oh, like. Is pi in there somewhere?
No.
It might be. I don't know the actual exact number. I just know the ballpark. Anyone know the ballpark?
Like 70, 66%.
It's like 66%.
Okay.
So even in the densest massive packing of spheres, it's 66%. But the key thing to remember with a liquid is it's a really dense fluid. Right? Every time you go into a room now, just imagine if we were liquid molecules, how many people would fit into this room? And the number is always a staggeringly high number. So that is why when we're dealing with low pressure vapor liquid equilibrium, right? Low pressure meaning we're not going to assume any non-ideality in the vapor phase in general. We have to consider non-ideality even with relatively simple molecular components, right? There's a table in the book that has a series of Van Laar coefficient, activity coefficient models. That's one I use pretty heavily because it's nice and convenient. But for all of those mixtures, you take a look, and there can be some fairly significant deviations from ideality, even for mixtures that you might think are just small, simple molecules, not even considering polymers and things like that. So let's start low pressure vapor-liquid equilibrium. So now what we're going to be doing is our governing equation here. In this case, the activity coefficient, which is a function of temperature, pressure, and composition, is not going to be equal to 1. It's going to deviate from ideality, which means that our starting point, if we assume ideal behavior in our vapor phase, this is the fugacity of species I in our vapor, right? It's effectively saying it's an ideal gas. Now this is going to be equal to a non-ideal mixture in the liquid phase. So we're not going to be able to neglect that particular activity coefficient. So anytime we're doing low pressure, non-ideal vapor-liquid equilibrium, it is critical, if at all possible, that we start with the liquid phase. Because if we are trying to do a dew point calculation, in a dew point, we know what the vapor phase composition is. And if we want to be able to calculate what the activity coefficient is, we also need to know what the liquid composition is. If we don't know what the liquid composition is, we can't evaluate the activity coefficient, we cannot evaluate this expression. So that turns what could be a relatively straightforward problem into a system of nonlinear equations, right? Because we would have to solve this to make sure that everything balances perfectly for all systems. So instead, our objective for low pressure vapor liquid equilibrium is to go from the liquid to the vapor phase. So just like the example problem that we had today, if we know the system pressure, the liquid composition, the activity coefficient, the pure species properties, we can just straight up calculate what the vapor phase composition is. Knowing what the vapor phase composition is, we can derive the dew curve based on the composition of the liquid phase from the bubble curve. Does that make sense, kind of? So if we think about ideal vapor-liquid equilibrium, and this is, you may think that I'm doing this just to be sort of beating a dead horse here, but I do go through this in my head every time I look at a phase diagram. Okay, A is the more volatile species. I want to look at a PXY diagram. So, should I draw my line here or here, right? So if I'm looking at A, it's the more volatile species. So at high pressure, it's a liquid. So at what pressure does it become a vapor? Right, so where should I draw my line? Because so the bubble curve is a straight line. Do I draw it down like this or do I draw it up like this?
Up. Yeah.
Why do I draw it up?
More volatile have higher saturation pressure.
Mean that it'll boil at a higher pressure. You don't have to lower the pressure quite so much. Okay, so that means that here, this is PA star, or saturation, and this is PB. So in normal Raoult's law, let's see if I did it. That's not too bad, okay. Right, Raoult's law for a bubble curve. Right, this is effectively just a weighted average of the saturation pressure, so it's a straight line. It's a linear function, right? Now, if we could consider that to a non-ideal system, and we can go through the math, but this is a pretty straightforward one to justify. Right, this will be the case if we have a non-ideal system. So, if I had derived my bubble curve here, right, let's say I'm at this point here. That means I know my liquid composition, I know my pressure. What I can do then is I can use Raoult's law to solve for my vapor phase composition. So we know that the vapor phase crosses the bubble curve, sorry, the dew curve. So just quickly walk me through this. So if I'm drawing a constant pressure line for the system, should my dew curve be here or should my dew curve be here?
Should be to the left.
Should be to the right, but why is it to the right?
High pressure will be liquidation.
So A is the more volatile species. So will the more volatile species have a higher mole fraction in the liquid or a higher mole fraction in the vapor or a lower mole fraction in the vapor? It'll have a higher mole fraction. So that means that my dew curve should be here. And I could repeat this process again and again, and I can draw my dew curve. Same concept applies for non-ideal vapor-liquid equilibrium. Once we know what the bubble curve is, we can use Raoult's law to connect the dots. Now the problem is a little bit that when you get over here, right, this line becomes pretty flat, so you have to add a lot of data points over here to get an accurate one. But that's trivial to do once you have computer code set up. All right. Just wanted to highlight that because I think a lot of people will make non-ideal vapor-liquid equilibrium problems a lot harder than it has to be. So let's consider two scenarios here. Because if you work from the vapor to the liquid, from the liquid to the vapor, it's really only a matter of adding one other simple function. Well, not simple function. It's a complicated one. Let's consider two scenarios. The activity coefficients are greater than 1. The activity coefficients are less than 1. So let's consider this first scenario. Activity coefficients are greater than 1. Does this mean that the fluids like each other or don't like each other?
They don't like each other.
Why don't they like each other? So how do I know that based on the bubble curve that's going to result? So if the activity
like what
coefficients are
it's gonna
greater
look
than
like.
1, should my bubble curve be like this or be like this?
Like the same,
Which way?
The same way you
Going
had, but like,
up or down? What deviation am I expecting? We can also look at our equation here, right?
it should go down. You should get like bigger pressures, or like. Let me think how to say this. I gotta think of this real quick.
Pressure goes up, then it would be out this way.
So let's break that. Okay, so at high pressure, what phase are we in?
Liquid.
Liquid. Okay, so for all the bubble curve, we're going from a high pressure to a low pressure, and we're trying to boil it. If activity coefficient is greater than 1, they don't like each other.
Yeah.
So does that mean that my bubble curve should be up here, or should it be down here?
Down there. Because they can get further away from each other if they're more in the vapor. Like the one wants to get out of the liquid where it's close to everything and into the vapor where it can have its own little party.
It's up here, actually.
Or okay, well, I'm thinking
Because
but I know what it should be.
I'm at a spot, let's say that's right here.
Okay.
I'm liquid. Now normally if I was a Raoult's law fluid, an ideal mixture,
T.
I would be like, okay, I can get along with these people. I can get along. Now I'm going to start to phase separate. If you really, really, really hate each other, you'll want to leave sooner at a higher pressure. Right, so this is going to be a positive deviation from Raoult's law. If the two fluids really like each other, they're going to want to stay liquid longer. In which case you're going to have negative deviation from Raoult's law. Your activity coefficient is going to be less than 1. They like each other. Right? Your excess Gibbs is going to be negative. Right? Because recall that the activity coefficient is related to the log of the excess Gibbs. Right? Negative excess Gibbs, meaning that the fluids like each other more than you would have expected based on an ideal mixture. Positive activity coefficient, positive excess Gibbs. The molecules don't like each other more than you expect. So then what we would do, if we had an activity coefficient model, we had a system mixture, we could calculate our activity coefficients. It's really an explicit calculation what we're doing now. Okay? We know the mole fraction of the liquid. because we're doing a bubble point calculation, because it's the total mixture. You're in the laboratory, you know how many chemicals you've mixed together. You have an activity coefficient model, even if it's really complicated, even if it has a lot of coefficients, even if it takes a calculator to execute, you have an explicit expression. You have the pure component saturation pressures. Those are tabulated, you can look them up, you can estimate them with an equation of state. You use this equation to calculate what the bubble pressure is. Once you know the bubble pressure, we have the saturation pressure, we have the activity coefficient, we have the liquid fraction, now we have the saturation pressure, which means that we can solve for the mole fraction of any species in the vapor phase. Which means that we could take some arbitrary point right here, and we could hypothetically come up with the composition of the vapor. Now, non-ideal vapor-liquid equilibrium, all bets are off. There can be a number of different shapes of curves. It can behave very counterintuitively. So we have to rely a little bit on organizing and tabulating the data according to activity coefficient models, because that's the best system we've come up with. And they can be very complicated, particularly when you look at the effective temperature. So there are some liquid-liquid mixtures, right? We would think that as you cool them down, they would phase separate, right? The hotter you get things, the more they'd like to mix. But there's actually a lot of liquid mixtures that as you heat them up, they begin to phase separate, right? So you have upper solubility limits in temperature, lower solubility limits in temperature. Every type of behavior that you can possibly imagine is probably been observed in liquid-liquid systems. Because the density is so high, there's so many interactions, it's really hard to predict how two molecules are going to behave. Now the key thing is that all of this, if we're living in a world of constant temperature and pressure, is that almost everything is going to be a battle between enthalpy and entropy. Now, as a general rule, entropy is going to want to make stuff mix. But you can also have systems where entropy wants them to unmix, right? So there's a very vast amount of complications going on here. It's not only the attractive and repulsive interactions, which are dominated by the enthalpic term, but it's also the packing and organization considerations in entropy. Now, molecules, you should visualize them almost as Lego bricks. But Lego bricks are very nice, clean, and organized. Molecules are not. And they also move and wiggle around and contort and change based on their environment. So estimating how they like to pack together and organize entropically is non-trivial and virtually impossible without advanced molecular level simulations. And even then, they're not particularly accurate. So we're getting into the territory now where it's really hard to handle all these different situations. So the best system, I know it kind of sucks a little bit, but the best system that we've come up with in thermodynamics is just to create a term and say, call it activity coefficient, and let's lump everything into that one term. And there's some pretty good activity coefficient models, but that's the key thing to remember. So we'll talk a little bit more about non-ideal vapor-liquid equilibrium, but honestly, this right here gets you a lion's share of the way through solving a lot of problems, particularly for this week's homework. Any questions? Okay, see you guys later.